A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Today we are going to talk about the semiconductor theory, the basic theory behind the widespread application of the semiconductors in the semiconductor industries. So this lecture is a part of nanophysics and technology course that has a course code of PHY445. In semiconductor theory, basically we need to know from the very beginning we need to know the band theory regarding the semiconductor, conductor and insulator. Normally, according to the band theory, conductors are those material which have almost no band gap. Band gap is actually the distance between the valence band maximum and the conduction band minimum. So in case of conductor, there is almost no band gap or very small band gaps, so that the electron can easily move from the valence band toward the conduction band and make itself readily available for the external potential difference. So this is actually the conductors from the basis of band theory of solid. If we look toward the insulator, then the insulator have the band gap, very high band gap, even more than 4 electron volt. So if you want to move an electron from the valence band toward the conduction band, you need huge energy for that. So therefore at 0K the valence band is completely filled and the conduction band is completely empty. So for the insulator, is hard to move an electron from the valence band toward the conduction band, and that is why if you apply an external potential difference, it is difficult. There are no free electron to move. So when no free electrons are available for movement, so that is why it has zero conductivity. Coming back toward the semiconductors, so semiconductors are in between conductor and insulators. There is a small band gap around 3 electron volts, or less than it. So that is actually the band gap in which at normal room temperature some of the electrons are capable to move from the valence band toward the conduction band due to the thermal energy. But if we look toward the 0 Kelvin temperature, so at that case the valence band is completely filled and the conduction band is completely empty. So that is actually the band theory image about the semiconductor. Today we are basically concentrating on the semiconductor theory, that why is so important for us and why the semiconductors are widely used in industries. So if we consider that at t is equal to 0, all atoms in solid to be in the ground states, so the distribution of electrons, that is actually electrons or fermions at the various energy level, is governed by the Fermi-Dirac statistic, and this is the equation to describe the Fermi-Dirac statistic, where B is a constant quantity that is equal to 1 over kT and EAF is the Fermi energy in this case. So this is actually the normal case of metals. So it's very easy for the electron to move from the valence band toward the conduction band, and at T is greater than 0. So coming toward the conduction, coming toward the insulator, we have coming toward the band gap of insulator. It is clear that the valence band and the conduction band have high energy gap. Each represent the gap between the valence band and the conduction band. So the Fermi level is in between the valence band and conduction band. So normally for insulated it is around 10 electron volts. So it's very hard for the electron to move from the valence band toward the conduction band. And this is the table for the semiconductor material, and the band gap is also mentioned, and even the values are mentioned at different temperatures. So here we have the band gap for energy gap for some semiconductor material, just like silicon, germanium and some compound semiconductor, which have varying band gap at different temperatures. So this is actually the band structure of the semiconductor materials. So small band gap is available, and this band gap enables the electrons to move from valence band toward the conduction band when there is at some room temperature. So some electrons are available in the conduction band while some holes are available in the valence band. When some external potential difference is applied, then the electrons are drifted in the opposite direction of the field while holes are drifted in the direction of the field. So that is why we have some electronic and hole current in this semiconductor material. A very interesting point regarding the semiconductor is that by increasing the temperature of semiconductors, the conductivity increases. It is due to the fact that increasing temperatures allows more electrons to move from the valence band toward the conduction band, thereby increasing the number of electrons in the conduction band, and only the electrons present in the conduction band contribute to the current. So similarly, in the opposite case, if we consider conductors, then the conductors, by increasing its temperature, its conductivity is reduced, because the lattice point vibrate or fluctuate with high amplitude with increasing temperature. So there is high probability that the electron will collide with the lattice point, and that will disturb, or that will create some problem or obstacle in the way of current, so thereby reducing the conductivity of that materials. So we have holes and in intrinsic semiconductor, holes and electron in intrinsic semiconductors. So holes, because normally if we consider the semiconductor material, so in that case, for intrinsic semiconductor, that is actually the pure semiconductor, the number of electrons should be equal to the number of holes, because as a whole this material is neutral. Whenever a single electron moves from the valence band toward the conduction band, it leaves behind a hole in the valence band. So normally for a intrinsic semiconductor material, the number of electrons should be equal to the number of holes, and both contribute to the current. So this is actually we have positive charge hole. The hole is moving in the direction of field, while electrons are moving in the opposite direction of field. So this is the applied field. Electrons are migrated from the valence band toward the conduction band due to the thermal energy. So as a result, this electron moves in the opposite direction of field, and the holes move in the direction of field. So we have electronic current and holes current, that is contribute to the total current of this semiconductor materials. So here the electrons are represented with this block diagram, the holes are represented with plus sign. Hole is nothing but that is actually the vacancy of electron. The missing electron is called as the hole in this case. So we have impurity semiconductors are extrinsic semiconductors are also possible. Extrinsic semiconductor is that we can increase. Why the semiconductor is interesting to us? That is only because of the fact that we can tailor the conductivity of semiconductor by doping. If we increase the doping, we can we can change the conductivity of this material, while in case of conductor, the conductivity is normally constant. So that is why doping is a way to change or tailor the conductivity of semiconductor material. Is possible with the help of doping, which is of two types, whether we dope a material that is a pentavalent or it is a trivalent. In case of pentavalent, that leads to an excessive electron, that is called as n-type material, while in case of trivalent, it leads to the vacancy or missing electron, that is called as a p-type materials. So this is an example of one of the whole intrinsic semiconductor. Keep in mind, when some impurity is doped in a pure semiconductor material, it will lead to impurity levels inside the band gap. And these impurity levels are created that are helpful to move the electron from the valence band toward the conduction band. So in this case, we have a type of stepwise transition of electron between valence and conduction band that will allow even low energy photon or even thermal energy photon to move the electron from the valence band toward the conduction band by this stepwise transition. This is the silicon, and arsenic is doped in silicon, and one extra electron is created. So extra weakly bound valence electron from AS lies in an energy level close to the empty conduction band. So this level donate electron to the conduction band. So this is one type of extrinsic semiconductor. we are coming toward the other type of extrinsic semiconductor, that are N type of semiconductor material. So the addition of arsenic, just like we consider the N in last case, there is a type of N type semiconductor material where it created or it donated a single electron, that is excessive single electron, while the total charge neutrality of the system is maintained. So because it is the electron close to the conduction band that will eventually carry electrical current. So this new this new arsenic energy level just below the conduction band are called as donor level, because this electron is the electron there is easily donated to the conduction band. We come toward the p-type extrinsic semiconductor material, in which there is a missing electron, or what we call as a hole. So this is actually called as a p-type material. When a gallium, that is from group 3, is added in a silicon, so what happened? There is a missing electron, and this missing electron is actually hole, and this acceptor level is created just above the valence band. That is also that also promote the motion of electron from the valence band toward the conduction band. But keep in mind the charge neutrality of the whole system is maintained. So these acceptor levels are created when indium is added to silicon. So indium has one electron in outer shell, then silicon. So what happens? The result is one extra hole per indium atom. So the existence of these holes create extra energy level just above the valence band, because it takes relatively little energy to move electron into a hole. These new indium levels are called acceptor level because they can be easily accept an electron from the valence band. Again, the result is an increased flow of electron as the electron move to fill holes under the applied electric field. So that will also create the current, and an increased number of holes will lead to the increased conductivity. So the majority carrier in this case are holes, while the majority carrier in the last case, that is for N-type materials, are electrons. So in this case, it is easier to think in terms of the flow of positive charges that are actually called as the hole in the direction of applied field. So this material are called as p-type semiconductor material, and the acceptor level is present in the p-type semiconductor material. So in addition to intrinsic and impurity semiconductor material, there are also some compound semiconductor material which consist of equal number of two kinds of atoms as well. So we have p-n junction. P-n junction is a type of diode which is created by bringing the n type of material and p type of material close to each other. So what happened? Initially, when the junction is made, there is a flow of electron from the n side, and flow of positive charges is actually gaining of electron in the p side. So what happened? When electron are leaving from the n side, each leaving electron leave behind a positive charge, and when a single electron enters the p side, each single electron create a negative charge on the p sides, and that is why at the junction a barrier is developed. The barrier is in such way that for n side we have positive side, and our p side we have negative side, and this is called as barrier potential, and this further stops the motion of electron from the n side that are actually the majority carrier in the n side, and the motion of motion of holes is actually due to the motion of electron but anyhow the motion of holes from the p side toward the n side, and that is why this junction is developed, which is called as a barrier potential, and the effect of this barrier potential is to stop further motion of the charge carrier. So this is some image of the p-n junction where we have some depleted region from mobile carrier. So this is actually the particular depletion region. So potential barrier prevent further diffusion of holes and electron, and zero current for no external potential difference. So once we apply an external potential difference, we can make the p-n junction as a forward bias or reverse bias depending on the attaching of the terminals of the battery to the p side and n side of the material. So we have rectifier as well, that is used for special purposes, that is used to rectify the electrical current. So in that case, it is a simple example of rectifications, where the current rectification I is equal to I naught e to power EV divided by KT minus 1. This is simple, and we can use the same P injection for rectification function. We can also use this P injection for the different type of applications. So rectification is one of the application where you can use this P injection in reverse bias mode and in forward bias modes, and the rectifications is performed. So we have recombination. In this case, in the forward bias case, what happens? The p-type material is connected to the positive terminal of the battery, and n-type of material is connected with the negative terminal of the battery. So as a result, the current moves through this through the barrier. Keep in mind, again, the potential difference, external potential difference, should be at least greater than the depletion potential that is available in between the n-type and p-types of semiconductor. Otherwise, the holes and electron will not overcome the barrier. So this is actually the reverse bias configuration of the p-n junction, where p-type material is connected with the negative terminal of the battery, and n-type is connected to the positive terminal of the battery. So that will not lead to the current, otherwise it will increase the width of the depletion region, and further, if we continuously increase the external potential difference, there might be breakdown occur that will rupture the barrier, and there will be no existence of semiconductor diode any further. So this is the reverse breakdown that occurs in the reverse bias configuration of the systems. Electric field is applied at zero bias, at reverse bias and forward bias, and the motion of electrons and hole is configured here. In the first case, electric field is applied, electron moves from n-type, and electron are drifted in such a way, holes are drifted towards from the p-type material. So as a result, current is there. The potential difference is EV naught, that is actually V naught is the potential difference of the barrier. For the case of reverse bias, we have the depletion region has been increased, and that depends upon the external potential difference. In this case, it is equal to E V naught plus V. This is another case, and at the that will lead to the stoppage of current. And in the forward bias case, we have the depletion, we have the potential difference that is available to E V naught minus V, that is equal to the that depends upon the external potential difference. But keep in mind, again I am telling you that the external potential should be at least greater than, to make the current move, the charge is slow, the external potential should be V should be at least greater than V naught. So this is the light emission from the diode, that is actually electric input to light LED, that is light emitting diode, and light to solar current is also available. So we can use the semiconductor material for different application. Just like when a photon is coming whose energy is equal to the band gap energy, so that photon will be absorbed, and as a result of this absorption, an electron will move from the valence band toward the conduction band, leading behind the hole. So this is the absorption process, and the photon cannot remain for longer time, the electron cannot remain a longer time in the conduction band, so it will come back toward the valence band, meeting with the holes, and that will create a photon. So this is the emission of photon process. So similarly, we have light to current in solar cells as well, where we can use the light for the current in solar cells process. So we have light emitting diode. This is a very simple light emitting diode, and that is important application of the p-n junction. When an electron makes a transition from the conduction band to the valence band, effectively recombining the electron and hole, so there is a release of energy in the form of photon, so that creates the light. So that is why we have light emitting diode. We have photovoltaic cell, the electron hole pair that are generated due to the absorption of photon, that are further used in the type of what you call as oxidation and reduction process of inorganic materials. So it can use this material for photovoltaic cells as well. So the electron and holes are created due to the photon absorption. So as a result, we can convert the solar energy for this, we can use for renewable purposes, for photovoltaic cell, for water splitting, and a widespread application of this photovoltaic cells. So we have superconductivity, that is also possible with the help of this thing, and superconductivity is the case where we have zero resistance for a materials. So in superconductivity, the electron flow without resistance. So superconductivity by itself is a vast topic, but anyhow we have introduced here just to have a basic understanding. So a Cooper pair, a pair of electron is moving, that is called as a Cooper pair, and that has the zero resistance is provided to this pair by moving the nuclei, by moving in between the nuclei, and that is a really interesting. And this Cooper pair is a type of attractive potential and repulsive potential, and that lead to a zero resistance. So we have this is electron is moving, and that the positive and negative charges come close to each other, and as a result this is moving. So this is something what we got about the semiconductor theory and the application of semiconductor in various application. Thank you very much for now.